So first, I'm going to look at products, the type of products we make. And we'll look at alkenes. So we'll start with alkenes. So let's think for alkenes, ways to add or create an alcohol. There are 3 ways to make alcohols that you know. There's 3 ways. Start this alkene. What kind of reagents make alcohols? What are the 3 ways? So the 3 ways: H plus in water, BH3, step 1, step 2, NaOH, H2O2, and the last way is that mercury O-acetate. Step 1. Step 2 is that in water. Those are the 3 ways. Now, if they all react with this alkene, they actually all give 3 different products. They don't give the same alcohol. Because there's a couple things that are different about these. This can do rearrangements. You're going to make a carbocation here. Carbocation, no carbocations. I'll write down the products for each of these. This is actually a catalyst, so it gets regenerated. Three alcohols, 3 different alcohols from the same starting material with 3 different sets of reagents. What's different here? You have a carbocation intermediate. This is an anti-Markovnikov product. This is a Markovnikov product. 3 ways to make alcohols, 3 different products. Markovnikov is just referring to, right, if I number my alkene, 1 and 2, 1 and 2, 1 and 2, 1, 2. You'll notice this obviously goes through a carbocation because there's a rearrangement. The only way you can do a rearrangement is if you have a carbocation. So this should tell you right away, you see this product, obviously there was a carbocation because something moved. Less substituted carbon is the anti-Markovnikov. More substituted carbon, call that the Markovnikov product. 3 ways to make alcohols. So let's talk about adding halogens. We know a couple different ways to add halogens. A couple things you need to be worried about or think about, right? What's below, if somebody's on the bottom of the arrow and there's not a number, right? Notice how it's different, there's not a number. If somebody's on the bottom of the arrow, what does that mean? What is that? That's a solvent, right? Water is a solvent in this. So we have 4 different types here. Let's see what the products are for all of these. All right, let's look at these 4 products about adding halogens. If we have this alkene, carbon 1, carbon 2, you'll notice what must have happened if I label this reaction A, this reaction B, C, and D. What happened in A? What can you tell me about the mechanism in A? There must have been a carbocation, right? Because something rearranged. There's carbon 1 and 2, so it must have gone through a carbocation. What about this one? Reaction B here, Br2 in water. Is there a rearrangement? No, there's no rearrangement. But notice you made an alcohol and a halogen. Right? You added an alcohol and a halogen. So when the solvent's around, right, you're going to add an alcohol. Notice what carbon did the alcohol add to? The more substituted one. Because this goes through that bromonium ion, that 3-membered ring. If we have Br2 with no solvent around, or at least not a polar protic solvent, but it's an aprotic solvent down here, what do? We add 2 bromines. If we have HBr with water around, notice again what happened here. carbocation, and we made an alcohol. So this really could go back to ways to add alcohols. So maybe this is kind of like the fourth way to add alcohols. Because the solvent's around, that's why that's going to play a role.
Should there be an extra like methyl?
Nope. Yep. So you probably noticed, right, there should be carbocation rearrangement, another way to make an alcohol, even with HBr around. All right, so really, here's a fourth way to make an alcohol. It's similar to up here, where it's just H+, right? Any H+, because really HBr is like H+ and Br-, right? HBr is a reactive strong acid, so it fully dissociates. And if you have solvent around, that's going to end up reacting because there's so much solvent. Goes to a carbocation. Br2, you get that trans addition too. Add 2 bromines. Br2 with a polar protic solvent. That solvent is going to end up on the more substitute of the carbons. There's 1, there's 2, there's 1, there's 2, there's 1, there's 2. Should have noticed with these, are there any carbocations with these? No carbocations, right? Because the stuff that you're adding ends up on carbon 1 and 2. If you had a carbocation, somebody's going to end up not on the alkene carbons. So there's your, this D right here is very similar to the first reaction before. Very similar to it. Here's 3 ways to add halogens. 3 ways to add halogens. One with a carbocation. One where you add 1, no carbocation, but the solvent's involved. One where you add 2, no solvents involved. Missing carbons. Should number all your carbons. All right, there they are. So those carbons didn't go anywhere. But yes, carbocation rearrangements. You'd get the bromine coming from the top and the bottom. Here, you'd get a trans addition, right? These OH and the Br would be trans to each other. These 2 Brs would be trans to each other. This is a carbocation, so you get both top and bottom products. So you know 3 ways to add halogens. 1, 2, 3. This is not a way to add halogens. It's the same. It's exactly the same as the first reaction with just H+. Because you can think of HBr as a catalyst here too, right? Because we regenerate it. So you know 3 ways to add alcohols. You know 3 ways to add halogens to alkenes. So right, making diols, 2 alcohols, not just 1. There's 2 ways to do that. And they have 2 different stereochemistries. One has the diols be syn or cis. The other has the diol be trans. One happens all in 1 step. One takes 2 steps. All right, one takes 2 steps. OSO4 gives us the syn diols. Plus, it's an enantiomer, right? What does that mean? All that means is the OH is being hatched, right? Not wedged, right? Because the hybridization state of carbon 1 and carbon 2 is sp2 hybridized, so they're flat, so they could react either from the top or the bottom. So you get this plus it's an enantiomer. See how there's syn, the 2 alcohols, the diol, 2 alcohols, or syn, plus it's an enantiomer. Next one goes through an intermediate. That intermediate is called what? Everybody knows what this is called? It's called an epoxide. This should become very relevant and remember this. Anytime you make a 3-membered ring, the next thing that happens is going to be a trans addition. Every 3-membered ring you make, Br2 with mercury or epoxide, the next thing you're going to do is a trans addition. It's always going to add from the opposite side, but you know that already. Why is it going to add from the opposite side? Because it's going to do an SN2 reaction. Where's sigma star? 180 degrees away from this. which would be, right, had to make a trans addition then. So if we had water, which carbon is water going to add to? 1 or 2? 2, why? More substituted. That's a fact. So why is it's more substituted, which means it's more able to stabilize the delta plus charge. Because it's more substituted, it can stabilize the more delta plus charge. That's that hyperconjugation. It's just like carbocations, but it's not a carbocation. Same idea as in carbocations, hyperconjugation, but it's not a carbocation, right? Everybody sees that? Not a carbocation. Because if it was a carbocation, would we get trans or would we get a mix? If it's carbocation, you get a mix, right? Because a carbocation, you can come from the top or the bottom. We don't get a mix. We only get trans. Do you also make this an enantiomer here first, in the first step? Yes, you do. So there's an plus enantiomer here. And a plus enantiomer here. Right? Those are the two ways you know to make diols. One is a syn diol. Both diols are wedged or hatched. The other is a anti or trans. You can also call this cis. You know, two ways to make diols, they give two different types of products. Because they obviously have different mechanisms. So just to review, right, this counts for anytime you have a three-membered ring. Anytime you have a three-membered ring, you go for the more substituted carbon. Whether it's Br2, mercury, or this epoxide. And the reason why you go for the more substituted carbon is because that's more stabilized by hyperconjugation, that delta plus, just like a carbocation. It's not a full plus charge, right? It's not a full plus charge. It's just delta plus, but we go for the more substituted carbon. And it comes, all right, an anti-addition. Get the anti-product. All right, last reactions for alkenes. Last ones. Cleavage of alkenes with O3, with ozone. O3. Two different ways you can do this. The first way, we call this the reductive method workup. And this one we call the oxidative method workup. Both have one product that's the same and one that's going to be different. Right? One that's going to be different. What happens with O3? Essentially, imagine taking scissors and you just cut along that alkene. You cut it and you're going to create two carbonyls. Two carbonyls. So this one we'll create that. And with this one, because it's oxidative, you turn that into a carboxylic acid. So you wanted to look for was these H's on the alkenes. Always a good idea to draw in the H's on the alkenes. So what happened? What's different here? In the oxidative workup, what happened? If you have an H on one of your carbons of your alkene, that H in the reductive workup stays. You get an aldehyde. Right? This is an aldehyde. In an oxidative workup, oxidative workup, if you have an H on carbon 2, it becomes an OH, and you end up with carboxylic acid. Oxidative workup, H2O2, right? Hydrogen peroxide versus dimethyl sulfide. Reductive workup is the easy one. Reductive workup, all you do is cut it, and nothing changes. There's H's, they stay the same. There's carbons, they stay the same. If you see hydrogen peroxide, that oxidative version, then you need to change these H's into an OH. That's all. So the other one for here is just going to be an aldehyde. In this one, replace those H's with OHs. Carbon 2, carbon 1, carbon 2, carbon 1. Oxidative workup, hydrogen peroxide, H2O2, replace the H's with OHs. Reductive workup, dimethyl sulfide, everything stays the same, you just clip it, you get whatever carbonyls there are. One last one, reduction, right? No mechanism needed here, no mechanism needed here, so these last three reactions there's no mechanism needed. Everything else you should know the mechanism for. This is adding H2. It's going to turn an alkene into an alkane. The biggest thing to remember here is that this is a syn addition. That you're going to add the H's if I put another carbon here. Right? You add the H's syn. In this case, N the enantiomer. So the H's always add syn. The H's add syn. Takes an alkene to an alkane. This is called reduction because we're adding hydrogen, whereas these are cleavage or oxidation. You're using O3. You're oxidizing things. All right, alkynes. Alkynes adding halogens. Four different ways to add halogens here. We have a terminal alkyne. So just like our alkenes, we should draw in hydrogens if they're there. We're going to end up going to the more substituted carbon, right? There's a carbocation type intermediate. Carbocation type intermediate. Usually this bromine and whatever H we added, right, would add trans. So if I circle this H, make it the red H, that H would be this one, and the H we added would be trans to the bromine. If there's excess, we just add two H's to carbon 1 and add both bromines added to the same carbon, carbon 2. If there's one equivalent of Br2, we go through a three-membered ring intermediate. Right? Br2, we get a three-membered ring intermediate, so we know the products are going to have to be what to each other? Trans, and they're trans to each other. If there's excess Br2, you're just going to do this whole thing again, and all these bromines are going to be added together. Two of them will be trans to each other. Right? All of them, these two would be trans, these two would be trans to each other as well. I'm not drawing this stereochemistry in, but you could imagine, right, these would be trans as well still. Questions? All right, so we're turning alkynes into carbonyls. What are carbonyls? Anything with C double bond O, right? Carbonyls anything with C double bond O. In particular, the two types here are aldehydes and ketones. You're going to make aldehydes and ketones. Which one of these reagents, A or B, makes aldehydes? Which one makes aldehydes? It's a 50-50 shot. B. BH3 does. That makes aldehydes. Just like before, right, you would call this an anti-Markovnikov product, like alkenes. Right? The stuff ends up on the less substituted carbon. BH3 is consistent. Ends up on the less substituted carbon. Mercury always gave you the Markovnikov product. In this case, what's the product going to be? A ketone. Ketone ends up on the more substituted carbon of the alkyne, carbon 2. You know one way to make an aldehyde and one way to make a ketone. There it is. These, right? Aldehydes and ketones from alkynes. Now let's take a step back and look at the intermediates each of those come from. Right? We call this the minor product. in between times, this is for set A, and B, you have these enols, right? You have these enols. You have these enols. Carbon 1, carbon 2, carbon 1, carbon 2. These enols tautomerize, right? They tautomerize, right? They tautomerize into carbonyls. One to an aldehyde, the other to a ketone. Two different mechanisms here, though, for this tautomerization. The first one involves H+. Notice the H+ is around. Should we use the H+? We should use the H+. So if I draw the H+, what's my nucleophile? The pi bond, hopefully everybody says. And at the same time, the OH bond electrons can form a new pi bond, right? Because how many electrons are in a bond? How many electrons in a pi bond? 2. How many electrons in a sigma bond? Still 2. So what did I do here? If I circle in blue this H, what does that H become? Becomes H+. Right? This taut. This is the tautomerization with acid. You get that H+, it's like a catalyst. Carbon 1, carbon 2. It might be easier for you to remember, right? Look where the OH ended up. In mercury with alkenes, where does the OH end up? On the more substituted carbon, right? Does the OH end up on the more substituted carbon here? Yes. It's just there's another pi bond here. Right? Because this is an alkyne. It has 2 pi bonds. With BH3 with alkenes, where did the OH end up? End up on the less substituted carbon? You bet. There it is. Right? You could even just draw this right away and then remember to do the tautomerization. That's the tautomerization with acid. What if there is no acid around? If there's no acid around, then all you do is take that H. Sorry, this is that circled blue H there. So there's the taut without acid. The H I have circled in blue here. Where does that end up? Anybody know where it ends up? Where does that H that's circled in blue end up? On carbon 2. Right, already had one H there. That's where that H ends up this time. To make an aldehyde. Aldehyde, a ketone. All right, reductions of alkynes. 3 different ways to reduce alkynes. The first set of reagents, you've already seen, H2 palladium on carbon. What's that going to do? It's going to keep reacting and turn an alkyne all the way into an alkane. So it's going to add 4 hydrogens. It's going to add 4 hydrogens. Lindlar's catalyst takes an alkyne and turns it into an alkene. But what type of alkene does it turn into? The cis. And the H's add sin. Stops at the alkene. Sodium metal and NH3, what does that do? Makes an alkene, but now it's going to be trans. So actually, it's going to be the same product. You can't tell here. Right? You get the same product here the way I have it drawn with a terminal alkyne. If I switch this to that, extra carbon, There you can see it. See that cis alkene, that trans alkene. Thing to remember, Na dot is different than, right? Na dot with NH3 as a solvent is different than Na NH2. Right? Don't confuse this with Na NH2. It's different. NH2 is different than NH3. So in these ones, right, E2 reactions to make alkynes, you're just going to do E2 reactions. So it'd be just like undoing, essentially, when you added 2 bromines with Br2 to the alkyne, or added with HBr and excess, added 2 bromines. It'd be just like undoing that, essentially. So let's see. Oops. NaNH2 2 equivalences. That means I can do how many E2 reactions can I do? 2, right? Each of these cases I have 2 leaving groups. They're going to give me the same exact products. Draw the alkyne first. If I added another equivalent of NaNH2, what is that going to do? That's going to then deprotonate my terminal alkyne, make it a nucleophile, and get it ready to do SN2 reactions. Do things need to be anti-periplanar for all these? Of course. Right? Make sure you get the bromine and the H trans to each other. Right? Make sure they're trans to each other. You're just doing an E2 reaction like you've done before. So the other byproducts of these, the byproducts are going to be, right, these bromines, right? Because this is really Na plus, NH2 minus. The bromines are going to form a salt. And there will be 2 NaBrs in both these cases. And the other byproduct is NH3 gas, right? NH3 gas is the other byproduct.